This is the 2025 Virtual Expo. It's the second edition of this online conference where we are going to celebrate and discuss progress that's been made in the League of Robot Runners competition. So our motivation here is that there are many new and emerging industrial applications, of course, that require the coordination of a team of robots. So applications like fulfillment centers, sortation centers, but more generally, any sort of application that involves autonomous vehicles, agents that have to work together in a team. So over here, we have sort of a simplified representation of how we often model these sorts of problems. So what's interesting, right, about many of these applications is that although the details differ, right, there are these core elements that are very similar across all of them. Often we model these problems as collaborative robots working in a grid environment, like we see here on the right. Regardless of the application, there's usually a set of errands that these robots have to run, right? So errands means that each robot has a particular set of goal locations that they have to reach. Of course, the plans must be collision free, and we're normally optimizing with respect to some objective, right? The objectives can be application specific, but the interesting part is that we're always trying to find efficient plans in these applications, and we're usually doing so online. So the clock is always ticking, there's always resource pressures, and of course, we're subject to operational constraints. So where the Robot Runners Initiative comes from, if this is your first time joining us, perhaps, I'll just give a bit of a background, right? So the idea is to develop a competition series to promote the study of multi-agent and multi-robot pathfinding. So solving these types of challenges that I was just talking about. So the goals of the initiative generally, okay, are to identify the core challenges in the area. And the way that we propose to do this, or some of the things that we would like to do, I should say, is we're interested in providing clear indicators of progress in the area, right? There's lots of work, and it can be overwhelming sometimes just to try and keep up with what's happening in the field. So the Robot Runners Initiative tries to provide clear indicators of progress in the area. We try to establish standard models and benchmarks, right? And standard interfaces and file formats. So this is about lowering the barrier of entry for people that are interested in working on and contributing to this area. We work to encourage and promote the release of open source baselines and benchmarks. So our first competition ran in 2023. We just had another competition that closed a few months ago, the 2024/5 competition, and we hope to continue this initiative over several years with increasingly diverse and realistic test beds. So the conference here today, the Virtual Expo, thank you again for coming. Right, so this is an opportunity for us to reflect and to celebrate on the most recent competition round, okay? So if you haven't already had a look at the schedule, here's a quick overview of what we're going to do over the next 4 or so hours. So we're going to have a bit of a look at what the competition looked like at the 2024/5 main round. We have 2 amazing keynotes for you. We're going to hear from Amanda Prorok of Cambridge University, and later on from Alexander Barbosa from Amazon Robotics. There'll be technical presentations from some of our successful participants. That's going to be amazing and always a highlight. We'll do reflection and we'll do awards, right? So we're going to present awards for distinguished performances. At the end, we're going to have a community meeting. So everything except the community meeting will be recorded and made available later on YouTube for subsequent reference or for people who perhaps have missed this live event. Okay, so let me do a quick overview of what we did in the 2024/5 competition. So this is here we have an example of the sort of problem that we're trying to solve. So the little blue dots that are moving around are the robots that we're controlling. Okay, so we have this team of robots that they're working together to complete tasks. Okay, the orange locations here, right? So their errand locations, I should say, right? So these are goals that each of the agents has to reach. All right. So a sequence of errands, okay, is is called a task in our competition. So let's have an example here, okay? So for example, we have these two errands here, right? So this task says that a robot has to visit first location number 1 over here, and then they have to go to the second location in the sequence. And after they've visited both of these locations, they've completed a task, okay? So you can think of this, the example here is coming from a sort of a simulated, inspired by an Amazon fulfillment center. But also many other sort of similar automated logistic applications, right? So this, you can think about this as a pickup and a delivery task. We're going from 1 to 2, okay? So that's one example of a task. Here's another example, right? So I've showed you the green task before. Here's a purple task. We start from the location number 1. We go to location number 2. Tasks don't have to be sequences of just 2 errands, right? Pick up and drop off. They can be sequences of 2 or more errands, right? So here's one that has 3. Okay, so what we do in the competition, right? I've just shown you 3 different tasks that have been revealed. Okay, so we know about them and we need to assign these to our robots in order to complete them. Okay, so in the example here, we selected robot number 51, lucky 51. And so we've assigned it the first task, the green task, right? So it's going to go, it's going to pick this package up over here, it's going to drop it off over there. And then it'll go on to do the second task, right? This 3 errand task, and then go on to finish the last task. Okay, so that's the sort of the high level idea. One of the challenges, of course, in the competition is planning, right? So the path taken to complete each task makes a big difference to performance in the competition. So here, for example, if the robot have taken this alternative path here, right, this might be better for improving performance. Another challenge in the competition is scheduling, right? So not just completing as efficiently as possible a sequence of assigned tasks, but also figuring out which robot should do which task. Okay, so this is important as well for performance. And so, at the moment, we've got everything assigned to robot number 51, right? But it might be better. Let's see if my slides work. Aha! We could say, well, what about robot 54 here, right? We could get robot 54 to complete the top task, okay? And working together, these 2 robots can complete all 3 of the tasks, obviously more efficiently than just one. We have a simplified but realistic setup, right? In the sense of what we're trying to do is we're trying to introduce additional complications that are featured in real environments, okay? But we don't want to go all the way to solving a very specific instance of the problem, right? We want to bring out the interesting core challenges in these realistic application settings. So we have these oriented agents in the competition, right? They can move forward, they can rotate left and right. There's certain kinds of collisions that we detect and we disallow, right? So they cannot occupy the same location at the same time. They cannot swap locations. There's some words here about the properties of the environment. It's fully observable. Everything's deterministic and known ahead of time. It's a centralized setup. Everything's collaborative. And of course, everything is running online, right? So from the moment that the simulation starts, the clock is ticking and performance is being measured throughout. There's no dedicated time for offline planning. In the competition, we had a relatively simple setup. So this is kind of a high-level overview, right? There was a central controller that controls the simulated world. And then there's these components over here, right? There's an infinite list of tasks. So as things are finished, new things appear. And basically, participants in the competition, right, were asked to implement either a path planning component, a task scheduling component, or both together in the combined track. Okay. So these are these sorts of problems, right? I sort of talked a little bit about the main challenges here, right? So in the planning track, we're really focusing on computing parts as efficiently as possible, right? So the task assignments are fixed. I should say there's a default scheduler that decides which robot does which task. And the job of the planner is just to complete the parts as efficiently as possible, so that everybody steps in the best way to reach their goals as quickly as possible. There's also scheduling, right? We talked about this just a minute ago. Which robot completes which task? Because robots have an orientation, and there's these rotation actions, right? There's some extra complications there when we do when we try and calculate how long tasks take to complete. So this is a sort of simplified example of typical robot dynamics that we find in the real world. Because the clock is always ticking, there's a trade-off in the competition between spending time thinking about better decisions and actually executing decisions, and making trying to make concrete progress towards the completion of each task. The problem is also online, which means that tasks are not known a priori. Okay, so we know only some of the tasks, and we only find out more as we go. If you didn't already know, I'm sure you do if you're here, but there is lots and lots of interest in these problems, right? Because of the explosion of interest from industry, there's been an explosion of interest in these kinds of multi-agent pathfinding problems across different communities. We see many works, for instance, coming from the planning community. We see many works coming from operations research. We see many works coming from computational geometry, robotics, machine learning. So there's a wealth of interesting and exciting work that's happening in this area.